Good afternoon. I'm Kentaro Hoshisashi, supervised by Dr. Kari and Dr. Paolo. I will talk about the physics-involved neural network for stochastic local volatility model calibration today. So to begin with the story, let me introduce the stochastic local volatility model. This is a combination of the two models. One is the local volatility model, and second one is the stochastic volatility model. So in combination, the first line showing the local volatility model, and second line showing the stochastic volatility model. These two are correlated with each other with the correlated Brownian motion. Then here's the problem that if you choose the local volatility, then you can reproduce the market option prices exactly, but that dynamics doesn't fit with the real market movement, become unrealistic dynamics. But if you choose the stochastic volatility model, you can generate realistic dynamics, but it fails to the match with the full volatility surface, real option market prices. So to solve that problem, the stochastic local volatility model called SLV model is introduced the new coefficient showing here called as leverage function L to combine the local volatility model and stochastic volatility model by introducing this component which are represented here and including the integral calculation to reach that. So here we need eventually we need a transition probability density to represent whole things. So that transition probability density P can be represented in the PDE formulation using the Fokker-Planck equation. So by Fokker-Planck equation, that SLV model can be represented here. It's kind of complicated formulation, and also it has derivatives of P with respect to the T and S and volatility V here, and also has some correlated each other. So by this Fokker-Planck equations, our goal is how to determine how to calibrate or determine the transition probability density function, which are three-dimensional value function, and also need to get the leverage function. It can be represented as here by calibrated density function P. So that is very kind of complicated problem in the quantitative finance because it's an initial value problem with pre-boundary conditions. But that solution uses both leverage surface and density P. But we need to think about more. So that P is a density function, probability density function. So that needs to satisfy several conditions which are related with the no arbitrage condition in the finance aspect. So of course that P is the probability density function. It should be positive, number one. And second is the total mass should be equal 1. That's usual. And then in finance perspective, it should be martingale. Martingale means it's the expectation of the underlying should be matched with the numeral and risk-free growth. So these three are related with the no arbitrage condition in the finance, and we need to calibrate the P and L, and also that P should satisfy these three conditions at the same time. That's a problem. So problem formulation. So standard calibration method do not automatically satisfy these conditions, of course, but usually researchers trying to solve by the numerical schemes like FDM, finite difference method, or Monte Carlo method. But it's really kind of like significant practical and computational challenges happened. So here is the kind of past researches, but many researchers are suggesting that some modification or some new idea from the many aspects, including the architecture-wise or computational-wise or the formulation-wise. But the main problem here is we need to calibrate the P and also L at the same time. So usually in numerical scheme, the main researches are usual general researches are taking these strategies. It's called the bootstrapping. So we don't know any P or L in the future time point, but we only know the P at the today because it's just one at this point. So then we can reproduce the L at the today, and then we assume that the L is not changing by the next time step point. After that, then we can get the P in the next time point. Then we can get then we can get the leverage function at the next time point as well. So that's a bootstrapping structure, but it has efficient but it's kind of sensitive noise and the signature biases happen. It's need kind of like a global consistency over through the time period, but it's fair to think about such a things. So on the other hand, we can think about the global optimization approach. So we can assume that we can get the probability function in any time point t, and then we can also convert it to the leverage function in any time point t. So then we can solve the p in p at any time point at once, and then we can compare to the that's obtained by value function is matched to the PDE or not. So that's a global optimization method, but it's really computationally expensive and kind of without any regularization techniques, it's kind of like it do not work well. So we are now trying to take artificial neural network approaches for this problem. So it can combine data fidelity with loss terms, and it enables smooth value function generation by the strategy to create the loss term function. So recently, using the physics-informed neural network approach is featured to solve such a complicated PD problem. So the original paper suggesting the adding the new loss terms, it's including the PD residual loss in their total loss function, like LF here. So by doing this, we can incorporate that the obtained neural networks can follow the PD equations by taking appropriate learning methods. So this approach can be extended to financial modeling, of course. And last year, we did some work for the more simpler PD problem called the local volatility model PD. So here, to solve the SAV model calibration using the pins, we augment the pins to enforce two additional integral constraints for the P. So we remember that the transition probability density function should match with the total mass should be 1 and should satisfy matching error property. So we introduced the more additional loss terms here, L mass and L matching error here. And also we introduced some modification to handle with the kind of like multiple loss terms balancing. So one thing is the self-adaptive sample weights. So we are fitting the weighting for the poorly fitting regions. And also we introduce a loss balancing for each loss terms should be balanced. And also we integrate to handle the additional loss terms, this L mass and L matching error. So this additional loss terms is also related with the no storage condition in the financial perspective. So it's kind of like very important principle for the SLB model calibration. So this is the whole architecture we take. So we employ the multi-layer perceptron to get to produce the probability function here, and also to get the Fokker-Planck PDE of SLB, we need to get the derivatives. So by doing the automatic differentiation, we can take each derivatives efficiently, and in parallel, we also do the integrals to get the leverage function, and also thank you. To check with the total mass condition or matching error condition. So this is the whole architecture. But here is the result. So in synthetic condition, here is the input local volatility surface, and also this is Heston parameters. And we compared with that of the benchmark method, which are here is employing the FDM method with ADI calculation. So here, that our proposal method can make the more smooth and reasonable surfaces for the leverage functions. So this is the pure transition probability density functions evolutions by the time. So it's kind of like similar to the benchmark method, but it's more like smooth and spread it out more naturally. This is the calibration errors for the accuracy, and in the synthetic data, our proposal method reduce the RMC over 95%, and also reduce sometimes for the real time data as well. So for the computational efficiency, our proposed method is also comparable runtime to benchmark. So overall, it's kind of like the durable for the using the artificial neural network approach for the SLB model calibration. So on top of it, we also check with the how if affect the additional loss terms of the total loss, total mass condition and matching error conditions. So this is the total mass investigation. The black line should be 1, and without additional loss term, then we got blue. But by adding the additional loss terms, that we can approach to the ground truth. And also a matching error side is also same tendencies. What we can see here is the by increasing the number of loss terms, usually make it a mess. It become complicated, but does not degrade overall model accuracy by using the loss balancing or self-adaptive weighting schemes. So this is conclusion. We propose the pin-based framework for the calibration for stochastic local volatility models using the Hooker-Planck equations. So the method to integrate constraints about the total mass or margin layers, and it's related with the no actual conditions. And our extended pin architecture achieves the lower calibration errors compared to benchmark methods on both synthetic and real data sets. So that's all from me. So thank you for your attention. And do you have any questions? Thank you.